Right. So let's imagine just for a sec, like a drop of food coloring, right?
Yeah.
Hitting a glass of water, like
Yeah.
perfectly still water. You're probably picturing that color kind of like slowly blooming outward, right?
Oh.
That's diffusion in action.
Exactly. Yeah. It's this like fundamental principle where molecules, they just naturally kind of migrate from where they're highly concentrated to regions where they're, less so. And it's happening all around us constantly, even if we can't always like see it.
It's like nature, like always trying to even things out.
Right.
But here's where it gets kind of cool, right? Today, we're not just watching this happen, we're going to try to decode it
Yeah.
using math.
Yeah, and the tool we're going to use for that is Fick's second law. And you can kind of think of it like a blueprint, I guess, that lets us predict how the concentration of a substance is going to change over time and across space.
A blueprint. That sounds a lot more precise than just watching dye swirl around.
Yeah. Fick's second law, basically, it tells us that the rate at which concentration changes, like at any given point, it's directly tied to how the concentration is changing right nearby.
Right.
So like an analogy, like imagine a hot cup of coffee cooling down in a room. The heat is going to flow from that hot coffee to the cooler air. And the bigger that difference in temperature is, the faster it flows. Fick's law is kind of similar, but for concentration instead of temperature.
Okay. I'm starting to get it.
Yeah.
But how do we actually, use this law, like a real world scenario? How do we translate, this blueprint into an actual building?
So let's imagine a scenario. Imagine a flat plate, and it's releasing some kind of substance into a still environment. Okay, so we fix the concentration of that substance at the plate, and we just assume that everywhere else has zero concentration initially.
So like a steady stream of dye coming from a flat surface.
Yeah, exactly. So now here's where the math gets a little more interesting. The solution to this diffusion problem, it involves something called the error function, which comes from statistics.
Wait, statistics? I thought we were talking about molecules here.
Right, and that's part of what's so cool about math. It often reveals these like surprising connections between, fields that you wouldn't think are related. So in this case, the error function, it gives us a really precise way to describe how the concentration of this substance spreads out from that plate over time.
So it doesn't just spread out like a simple ripple effect then?
Not quite. The error function lets us define something called a concentration boundary layer. And that's the region where the concentration is significantly different from, that initial zero state.
Okay, so it's kind of like a zone of influence where the substance is, making its presence felt around the plate.
Exactly. And here's where it gets, I think, even cooler. This boundary layer, it doesn't just expand at a steady rate. It actually grows in proportion to the square root of time.
Hold on, so you mean it's spreading out but slower and slower as time goes on?
Right.
Why wouldn't it just spread out evenly?
Well, that's a great question. It really kind of highlights how diffusion, even though it's always striving for like this equilibrium, it doesn't progress in a simple linear way. The initial stages of spreading are much faster.
Wow, we've gone from like a single image of dye in water to talking about error functions and expanding boundary layers. It's my brain is definitely working now.
Yeah, but we're just getting started. The real power of this mathematical framework is that we can use it to answer like practical questions. For example, how much of that substance has actually diffused out from that plate at a specific time?
So we're going from that blueprint to actually calculating how much, building material we'd need.
Exactly. So to answer that, we have to think about the flux, which is basically the flow rate of the substance. How much is moving, across a given area per unit of time.
So it's not just about how much is there, it's about how fast it's spreading.
Right, exactly. The formula for flux, it takes into account the concentration difference, the time elapsed, and also the diffusivity of the substance, which is basically like how easily it moves through whatever medium it's in.
So there's a lot of variables at play.
Yeah, absolutely. But that's what's kind of elegant about this formula, right? It captures all of those factors, in a pretty concise way. It gives us a really powerful tool to quantify the diffusion process.
This is making me think differently about like all these tiny molecular movements happening around us all the time.
Yeah.
Well, I'm ready to keep going, but maybe let's just pause here for a minute. I want to make sure everybody listening has time to, absorb all this.
Super. Welcome back. Glad you're sticking with us. So before the break, we were talking about like the mathematical kind of foundation of diffusion. Now I think we should, try to see how these equations actually translate into real world stuff.
I'm starting to see like those dye swirls everywhere now, right?
Mhm.
In my coffee, and the way smoke rises, like how a scent travels across a room.
Yeah.
It's like I have a new way of seeing things.
Exactly, and that's the power of understanding these basic principles. They give us this framework for understanding these like seemingly really complex processes.
Okay, so let's talk real world scenarios. Where does this mathematical model of diffusion, where does it actually come into play?
Well, let's start with something we're all familiar with. Scent, right? So imagine you're baking cookies. The aroma, those cookies spreading through your kitchen, that's diffusion.
Yeah.
But have you ever noticed how some smells, they kind of linger longer than others?
Now that you mention it, yeah, like the smell of cinnamon seems to stick around forever, long after the cookies are gone.
Hmm.
But like a lighter citrusy scent, it fades away way faster.
That's a great observation. And it all comes back to diffusion, right? The size and the weight of those aroma molecules, it actually determines how fast they diffuse. Heavier, more complex molecules like cinnamon or vanilla, they diffuse more slowly, so the scent lingers, right?
Okay.
But lighter molecules, like the ones that give you that citrus scent, they diffuse faster, so the smell fades quicker.
Oh, I never thought about it like that, but it makes sense. So even in something as simple as like the smell of cookies, there's this whole like intricate dance of molecules happening.
Right. And once you start to kind of look for it, you'll see diffusion everywhere. Take pollution, for example, like a smokestack, releasing pollutants into the air. Those pollutants, they don't just stay put. They diffuse outwards, carried by, wind and air currents.
So it's like an invisible plume kind of spreading out from that source.
But it's not a uniform spread, right? We talked about that, like concentration boundary layer expanding over time. You got it. And understanding like how fast and in what pattern those pollutants are diffusing, it's really important for environmental protection, right? Scientists, they use these like really sophisticated models, a lot of them based on Fick's law, to try to predict how pollutants will move. And to assess, the potential risks, they consider factors like wind speed, temperature, even the chemical properties of the pollutants themselves, because those all affect how they diffuse.
It's incredible how something we can't even see can have such a huge impact.
Yeah.
It makes me wonder about like other invisible processes that are happening inside our own bodies. Does diffusion play a role there?
Absolutely, yeah. I mean, diffusion it's essential for life itself. One really critical example is drug delivery. So think about like a transdermal patch, the kind that you use to deliver like nicotine or pain medication. The drug molecules in that patch, they're diffusing through your skin and into your bloodstream.
So the patch is like our flat plate, releasing a substance at a constant rate, right?
Right.
And Fick's law helps us calculate how quickly those molecules are getting absorbed into the body.
Exactly, yeah. And by understanding like the diffusion properties of different drugs, scientists can design patches that deliver the right amount of medication at the right rate, so you get optimal treatment.
This is blowing my mind. I had no idea diffusion was so important in so many things, from like the smell of cookies to pollution control to even how our bodies absorb medicine.
Yeah, and we're just scratching the surface here. Diffusion isn't just about the movement of molecules. It's a universal kind of principle. It shows up in places you might not expect, like the way ideas spread through a population. That can actually be modeled using diffusion equations.
Wait, you mean like how rumors spread or how trends catch on?
Yeah.
That's similar to how molecules move?
It might sound strange, but mathematically there are these really striking similarities. So think about how a new idea gains traction. It starts with a small group of people. Then through interactions and communication, it spreads to a wider and wider population. And that's actually pretty similar to how molecules diffuse from an area where there's a lot of them to an area where there's fewer.
I'm starting to see the world in a whole new light here. It seems like every process is kind of governed by this invisible hand of diffusion.
And the more we understand about these fundamental principles, the more we can appreciate the connections, the connections that make up our universe. But there's one more aspect of diffusion that we need to talk about, and it might be the most interesting one yet.
Okay, you've definitely got my attention now. What else is there to learn about diffusion?
Well, so far we've been talking about diffusion as if it always follows the rules, right? The rules laid out by Fick's law. But what happens when those rules get broken?
Broken. How can a fundamental law of nature, how can it be broken?
Well, it's not that the law itself is wrong, but But the environments where diffusion happens, they can be really, really complex. And sometimes that complexity leads to behavior that's different from the neat, predictable patterns we've been talking about.
Okay, now you've really got me intrigued. Tell me more about this rule-breaking diffusion.
That's where we're going next. Get ready to dive into the world of anomalous diffusion, where the unexpected, it kind of reigns supreme.
Get ready, anomalous diffusion. Sounds like we're going off the map here.
Yeah, you could say that.
Yeah.
So far, we've been talking about diffusion in, fairly simple environments. But in the real world, things aren't always that neat and tidy.
How do you mean?
Okay, think about trying to walk through a crowded room versus like an empty hallway.
Okay.
In the hallway, it's straightforward, right? You just walk straight through.
Yeah.
But in a crowded room, you're constantly dodging people, changing direction, maybe even getting stuck for a bit.
Yeah.
Your movement is a lot more, erratic, less predictable.
Yeah, I can see that. So are you saying molecules experience something similar?
Exactly. So in these more complex environments, crowded environments, the way molecules move, it can be, hindered or even sped up in ways that don't follow that simple square root of time relationship we talked about before. And that's what we call anomalous diffusion.
So instead of that smooth, predictable spread, it gets a little messy.
Exactly. Sometimes the spread might happen way faster than you'd expect, and other times it might be incredibly slow. It really just depends on the specific environment and how it's, affecting the molecule's movement.
So does that mean Fick's law,
Right.
it doesn't apply anymore in these situations?
Not necessarily. Fick's law still gives us the basic framework, but we have to adjust our mathematical models to account for this added complexity. Think of it like Fick's law gives us the rules of the game, but with anomalous diffusion, we're playing on a much more complicated playing field.
So where do we actually see this anomalous diffusion? What kinds of systems are we talking about?
It's more common than you think. You see it in, the movement of proteins inside a cell, which is a very crowded environment.
Oh, yeah?
The transport of contaminants through soil, because the soil has all these intricate pathways that can, create obstacles. Even the way financial markets fluctuate, because information, it spreads and bursts and jumps, not in a smooth, continuous way.
Wow. So how do scientists even begin to study something that seems so random?
It's a challenge, for sure, but researchers are, they're developing new tools and models all the time to try to capture this nonlinear, unpredictable behavior. One approach is to use fractal geometry, which is a way of describing these complex, irregular shapes that have repeating patterns at different scales.
Freckles, like those infinitely repeating patterns you see in nature.
Exactly. And it turns out those fractal patterns, they often reflect the underlying processes of anomalous diffusion. So by incorporating fractal geometry into our models, we can start to make sense of this, seemingly chaotic behavior.
This is really stretching my brain here, but in a good way.
Oh,
It feels like
probably.
we're uncovering a whole new layer of how things work.
Yeah, and that's what makes science so exciting, right? The more we learn, the more we realize how much more there is to discover. And anomalous diffusion is a perfect example of that. It forces us to come up with new ways of thinking. It challenges our understanding of how the world works.
Well, this has been a wild ride. We've gone from, simple die swirls to the complex math of diffusion. We've talked about real world examples. And we even explored this mind-bending concept of anomalous diffusion. I feel like I have a whole new appreciation for, the invisible forces that are shaping everything around us.
I'm glad to hear that. And remember, this is just the beginning. There's still so much to learn about diffusion. So stay curious. Keep asking questions. And who knows what you might discover.
Thanks for joining us. We hope you enjoyed the journey as much as we did.